Yes, you're welcome back. Mr. Hyper welcomes you. This is me, and you subscribe to my YouTube channel, Hyper and Chuo Academic channel. Also, you can WhatsApp me just in case something goes wrong at +256, showing that I'm Ugandan, 7591932660. There we can have some great jazz about this simple chemistry. So, this time around we are recording for organic chemistry, and we are specifically looking at methylbenzene. In our previous video about organic chemistry, we looked at the reactions that are undergone by benzene itself. So this time we are looking at its derivative, and that derivative interested in is methylbenzene. So methylbenzene, one can call it toluene, and it takes on very many properties of benzene. It has got molecular formula. Methylbenzene has gotten molecular formula C7H8, and it has gotten the structure formula of we draw a benzene ring first. You can draw bonds and then you put CH3, or still you can draw a benzene ring, then you put CH3. So that is all about methylbenzene. And for organic analysis, or rather for organic chemistry, the moment we talk about a certain group, we want to also look at how to obtain that group, what we call synthesis. Then we go ahead to look at the physical properties, the chemical properties which involve the mechanisms or the role taken when these molecules or compounds are reacting. Then we talk about organic analysis where possible. So for this case, we are going to look at how to obtain it, preparation of methylbenzene. So allow me put a dash line and say preparation of methylbenzene. Why called methylbenzene? It's called methylbenzene simply, actually it is one word, methylbenzene, simply because a methyl group is directly attached to the benzene ring. So methyl, a methyl group, CH3, a methyl group. So in other words, you know the structural formula of benzene, rather the molecular formula of benzene is C6H6. But the fact that we are attaching another carbon, that's why another group, methyl group, which contains a carbon, that's why the carbon has become C7. Then this substituent, the methyl group, substitutes one of the hydrogens, meaning the hydrogens are 5, but when you add these 3, they become 8. So that's why it is C7H8, just as simple as that. So let's look at preparation of methylbenzene. We can get methylbenzene from benzene itself. And how do we get methylbenzene from benzene? We bubble chloromethane. Since we need methyl, so chloromethane through dry benzene. Okay, in presence of a catalyst, which is anhydrous aluminum chloride catalyst at a temperature of 40 degrees Celsius. So here we have our dry benzene. Okay. We shall bubble chloromethane CH3 Cl in presence of anhydrous aluminum chloride, which acts as a catalyst, at a temperature of 40 degrees. And this one gives us methylbenzene CH3 plus HCl. This process is what we call alkylation of benzene. This is alkylation of benzene. And under benzene, we looked at how this mechanism is possible. So let me outline it again for you to remind you mechanism for that reaction. We shall have CH3 Cl with aluminum chloride. So this one will give us, one can use double alloys, partial double alloys, to give us a methyl. After removing the chloride, it becomes positive. And then aluminum chloride intermediate. But this one is an electrophile. And being an electrophile means that benzene will undergo electrophilic substitution, whereby in electrophilic substitution, the hydrogen in the carbon atom, rather in the benzene ring, is replaced or is substituted by an electrophile, which is a methyl. So shall have a methyl group here. So being an electrophile means it is electron deficient, so it is given electrons. This one will lead to the formation of a plus. Here we shall have a plus because an electron has been removed, so we shall have a plus with a methyl, which will be momentarily attached, but this bond of hydrogen will stabilize the ring, and by loss of a proton, we shall form methylbenzene. Alternatively, since we have CH3 Cl, it's going to react with the aluminum chloride. One can write it like this, forming and an intermediate. One can say partially negative, partially positive. Now, during the reaction, this one, which is an electrophile, the one which is going to participate, so we are going to have CH3 with a plus, right? So this is and after this, we shall have that methyl group momentarily attaching itself. I can use a partial circle One may meet this one somewhere. Then we have our hydrogen and a methyl. Then there we bring our aluminium chloride intermediate to attack the hydrogen as the hydrogen stabilizes the ring, leading to the formation of methylbenzene plus aluminium chloride, and then hydrogen chloride. So that is what we would have. So that is the first reaction. That is the first reaction. Then the second reaction that gives us methylbenzene is from bromobenzene. We can get methylbenzene from bromobenzene. One may wonder how. One may wonder how. This reaction, we can also call it fittings reaction. And under fittings reaction, sodium metal is added slowly to an ether solution, containing bromobenzene and iodomethane. Resulting in the formation of methylbenzene as the main product. So in this reaction, we have bromobenzene we add iodomethane and sodium metal, then in presence of ether, so this reaction leads to the formation of our methylbenzene, sodium iodide, and sodium bromide. But when we are synthesizing, we specifically talk about the main products or the major products. One can simplify this equation by writing bromobenzene. We have iodomethane, sodium, and dry ether. So still, you're going to form your methyl benzene. So this is what we call fittings reaction. Iodomethane in sodium, sodium in iodomethane in presence of dry ether. So we've got a third reaction, not very common, but it also gives us the product. And this is on industrial scale. So on industrial scale, we prepare it by heating methylcyclohexane under high pressure in presence of molybdenum 3 oxide and aluminium oxide as a catalyst. So we have methylcyclohexane heated, okay, under pressure. So we have temperature 560 degrees Celsius, and under pressure but it is affected by molybdenum 3 oxide, molybdenum 3 oxide, that is M2O3, and the aluminum catalyst, rather aluminum oxide, so Al2O3. This is a catalyst, and this reaction yields methylbenzene. This is methylbenzene and hydrogen gas. So that's the reaction that can give us the product. Now, from here, I want to specifically take you through the properties of methylbenzene. And we are going to begin with the physical properties. And because it's a derivative of benzene, it means that it has gotten some physical properties which makes it different from benzene. So physical properties of methylbenzene, but I want to bring it out as different in terms of differences, right? So let me say here benzene. Let's have benzene here, and let's have methylbenzene here. Right. So this we can have a simple comparison, and the first one I want to bring it as melting, in terms of melting points. So benzene has a higher melting point. We shall see the reason. Has a higher melting point, and that melting point of benzene is 5.5 degrees centigrade or Celsius. But this one has a lower melting point, and it is as low as -95 degrees Celsius. When it comes to boiling points, now this one has a lower boiling point, as low as 80 degrees Celsius, but this one has a higher boiling point, which is as high as 111 degrees Celsius. Toxicity levels, this is benzene is highly toxic, whereas methylbenzene is less toxic. Yeah, it is less toxic, you can take that. But both are insoluble in water, but soluble in organic solvents, right? And they are good organic solvents, really. Then both are colorless liquids. Yeah, actually methylbenzene quite much resembles benzene. So our main issue is to talk about their melting points. The melting points. Methylbenzene has a lower melting point, okay, but that of benzene is higher. Okay, so methylbenzene, want to see the reason why methylbenzene is having a higher melting point? Simply because when you look at benzene, it is all about their structures. So benzene structure is planar. And the planar molecules of benzene can pack more closely together in the crystal lattice, okay? And then cohesive forces become stronger. The molecules of benzene planar. Someone may need to know what we mean when we say planar molecules. When we say that planar molecules, it means that it is relating in terms of a plane. For example, basically, when we say like a square planar molecular geometry, molecular geometry of some compounds, we are looking at the spatial arrangement. Okay, we are looking at the spatial arrangement. So, if you look at benzene, is planar, consisting of, before I draw the bond, consisting of 6 hydrogen atoms, and the carbon atoms are bonded to each other in a regular hexagon, and each of the hydrogen atom is bonded to a different carbon atom. They are also arranged in a regular hexagon specifically. So we say that benzene molecules are planar because now this one takes us to hybridization. It takes us to clear hybridization, but we need to know that all the carbon atoms are sp2 hybridized. I will not go into the details of that, but you have to remember that if carbon has an sp hybridized molecule, then it will show linear. For sp2, it shows planar, and for sp3, it shows 3-dimensional geometry. But the fact that the benzene molecule is planar, let's consider it planar. Its molecules are closely packed, and that close packing makes the cohesive forces between the benzene molecules very strong, while methylbenzene molecules are less closely packed, meaning that the forces of attraction between benzene molecules are very strong to be overcome, thus requiring a melt at a higher temperature, while for methylbenzene, the forces of attraction between the molecules are weak. Now, that is the main thing, whereby we have said that the planar symmetrical benzene molecule can pack closely together in a crystal lattice, hence having stronger cohesive forces than methylbenzene molecules, in which the methyl group makes the methylbenzene molecule prevent such close packing. So the methyl group prevents the close packing in methylbenzene, while for this case, there is nothing stopping cross packing from taking place. All right, so that is one of the the notable factor or the notable physical property that we can discuss further. Well, another thing we should know about methylbenzene, I want us to discuss about the inductive orientation. Let me call it inductive orientation on benzene ring in relation to methyl group. Now, like benzene, this methylbenzene also undergoes electrophilic aromatic substitution reactions. For example, sulfonation, nitration, halogenation. It undergoes all acylation. It undergoes all electrophilic substitution reactions like benzene. However, here we shall be producing different products. Okay, so these different products are named using the prefixes, where we are going to find, you're going to be using the ortho prefix, you're going to be using the meta prefix, you're going to be using the para. So we have orthopara and meta. Now, we are going to, let me first summarize for you the isomeric products of the ortho meta para notations. For example, if you have methylbenzene, we have not yet looked at the reaction, but let me bring it here. If you have methylbenzene, CH3, maybe it undergoes sulfonation, fuming sulfuric acid. It is going to form different products. And it is going to form with a sulfonic group here. And it can also form so it will form 3 isomeric products. It can also form CH3, then let's go 3H. This is 32%. This is 62%. And this is just 6%. Now, what does it mean? This one here is a 2 substituted isomer. It forms 3 isomeric forms. So this one is a 2 substituted isomer, whereby the electrophile substituted the hydrogen on the second carbon. This is a 3 substituted isomer, in that the electrophile substituted the hydrogen on the third carbon, and this is the 4 substituted isomer. Now, the 2 substituted isomer, this position is what we call the ortho. Ortho. This is ortho, the second position. So when you form a 2 substituted isomer, this is called ortho methylbenzene sulfonic acid. Methylbenzene sulfonic acid, one word. Some books, you'll find them calling it O methylbenzene sulfonic acid. When you substitute on the 3rd or on the 3, this is called the meta methyl benzene sulfonic acid. Methylbenzene sulfonic acid. When you form on the 4th, we call it para. So this is para methyl benzene sulfonic acid. It means that the substituent is on the 4th carbon clockwise. Now, from this equation, the orthopara isomers are formed in large amounts than the meta. So we shall always find that our main products are going to always be this and this, because of by just basing on this reaction of sulfonation, the product is formed in on the ortho and the para in large amounts compared to this. Now, similarly, even if you consider nitration, Friedel-Crafts, alkylation, acylation, and the halogenation of methylbenzene, it will give mainly the ortho and the para isomers, all right? And the reactions are faster than it would be for benzene. So we are going to look at the reason why methylbenzene is more reactive than benzene itself, because we are saying that the reactions, all those electrophilic substitution reactions, are faster for methylbenzene than for benzene. What I'm trying to mean is that for all reactions, just like that sulfonation, even other reactions methylbenzene, much as we've not looked at the properties, but if you have methylbenzene, even if it is nitration, nitration takes place in presence of conc nitric acid and conc sulfuric acid at a temperature of 55 degrees Celsius. Still, we are going to form the orthopala. So it will be CH3, then NO2. Because in the nitration of benzene, actually, in the previous video, we looked about benzene. So benzene, nitration, the nitro group substitutes the hydrogen. Now, you form this, then also you form this. So we form a 2 substituted isomer and a 4 substituted isomer. So one can name this as 2-nitro methylbenzene. 2-nitromethylbenzene, or because it is on the ortho, one can call it O-nitromethylbenzene. Nitromethylbenzene. Then this one can call it 4-nitromethylbenzene, meaning that the substituent attached is on the 4th carbon. Or one can call it P, that is para nitromethylbenzene. Then also the same reaction can take place for alkylation. Alkylation takes place in presence of Friedel-Crafts catalyst. So if we have a methyl and maybe we add chloroethane, that is an alkyl halide. So when you add chloroethane, we are going to look at the details of the mechanisms again. So in presence of aluminium chloride, this one will give us still ortho and para product. So we shall have CH3 here. We are attaching CH2, CH3. We are attaching the ethyl group. Then plus another product, which is a para, CH3, then CH2, CH3. So it is even for acylation, an acid bromide acylation. So we need a halogen in presence of maybe a Friedel-Crafts catalyst. It's going to give us still CH3, then CO, CH3 plus, still you can have a 4 substituted isomer, CH3 here, COCH3. Even if it is halogenation, still it is going to have, we are going to have CH3 halogenation, we shall have chlorine in presence of the catalyst, aluminum chloride. Most of these reactions, if you remove a methyl group, we looked at them in benzene. So we shall have CH3, then an electrophile attached on the 2nd carbon. And then here we shall have it attached to the 4th carbon. Cl, sorry, this is Cl. So this one shows that all these reactions imply that the methyl group is an ortho-para directing, O2,4 directing. The methyl group is an ortho-para directing, meaning that all these reactions, we shall always be getting our product as a 2 and 4 substitute. So 2,4 directing. So it is 2,4 directing group. We need to know that methyl group is a 2,4 directing group. Now, we want to discover why is this methylbenzene more reactive compared to benzene? Now, methyl group is the main thing we are looking at in this reaction. We are having a methyl group but methyl group donates electrons to the benzene ring, implying that when electrons are pushed to the benzene ring, the electron density in the benzene ring has increased. And the more the electrons, the more the reaction, or the higher the reaction, sorry. Now, methylbenzene in simple terms is more reactive than benzene because the methyl group donates electrons towards the benzene ring, making or increasing its electron density and making it more reactive towards electron deficient species, meaning that the species which are electron deficient, those are electrophiles, are going to find this one when it is full of electrons. So electrons are easily given to those electron deficient substances or electron deficient species. Now, you need to also know that if sulfonation is discussed before it is carried out for nitrobenzene, the reaction is slower for benzene, and mainly the metal isomer is formed. We are going to look at also nitrobenzene as the substitute on its own, but you need to know that the nitro group, unlike the methyl, the nitro group is a meta. It is a meta-directing. It is a 3-directing group. Okay, so that's why we say that nitrobenzene is less reactive than benzene, because the nitro group now for it withdraws electrons. Now, if you compare the reaction with the one of a nitro group, now for a nitro group is electron withdrawing, so it withdraws electrons from the benzene because of that nitro group, which is electron withdrawing, meaning that the electron density of the benzene ring is going to be decreased and thus less reactive towards the electrophile. Therefore, we are going to find out that any group attached to the benzene ring affects the reactivity of the ring and determines the orientation of the substitution, right? Now, even if it is the OH, if it is phenol or hydroxybenzene, still the reactions are going to be different. We are going to be looking at all these types of reactions, but specifically for now, we are looking at methylbenzene. A methyl group is electron donating, so it donates electrons to the benzene ring, increasing the electron density in the benzene of the benzene. Thus, electrophiles makes it more reactive towards the electrophiles or the electron deficient species. So a group that makes more reactive than benzene is an activating group, and a group that makes the ring less reactive is called a deactivating group, meaning that a methyl group is an activating group because it makes the ring more reactive. But a nitro group, on the other hand, is deactivating group because it makes the ring less reactive towards electrophiles by withdrawing electrons from it. Very interesting. So there are very, very many other things we shall be looking at, but for now, let me switch you direct to chemical properties. Chemical properties. Of methylbenzene. Now, this methylbenzene, it will undergo 3 types of reactions, or it undergoes 3 types of reactions. So it undergoes electrophilic substitution like benzene. undergoes electrophilic substitution, it undergoes substitution in the methyl group, it undergoes addition reactions. So we are going to specifically begin with let's begin with, since we have already covered benzene, let's begin with electrophilic substitution reactions. Electrophilic substitution reactions. Now, an electrophilic substitution reaction simply occurs in the benzene ring, and the methylbenzene reacts with all electrophilic reagents. And each reaction, it is more reactive than benzene, because we have already seen that the methyl group is an activating group. It donates electrons to the benzene, making benzene have high electron density, making it more reactive towards the electrophiles. So in each electrophilic substitution reaction, methylbenzene is more reactive than benzene. All right. Now, we are going to find that all products, because a methyl group is 2,4 directing, we shall be forming the products with an electrophile on the second carbon and the fourth carbon. So let's begin with halogenation. Halogenation. In the ring. Okay. Now, like benzene, also methylbenzene will react with either chlorine or bromine in presence of iron 3 chloride, or it can be aluminum chloride catalyst at room temperature to form the products of 2-chloromethylbenzene or 4-chloromethylbenzene, as we saw. So we shall have chlorine, we form Cl plus no, we form on the fourth Cl. So then plus 2HCl. The same applies if one uses bromine. Still, you can say bromine, whether methylbenzene, or you can now change, you can use another, you can use like aluminum bromide. Still, you are going to form an ortho and para plus I don't know why I'm too much in love with the second position. Then plus HBr now, be HBr. Now, looking at the mechanism, or it can be also written as, if you have this, also this one works, you'll get, now it means that if the CH3 is here, the bromine will be here, plus still this one keeps here. Now your para will be here. So let me outline a simple mechanism for this. A simple mechanism for this. These mechanisms take the form. They take the form of those mechanisms of benzene. So what happens is that we shall have chlorine reacting with iron 3 chloride from chlorine and iron chloride intermediate. So we're going to have CH3 then we shall have so this one will come and this one goes, forming, or since I'm going to form 2 different products, I can have it like this. CH3, my H, the chlorine has momentarily attached itself there. The same applies here. I have H, I have Cl, I have CH3. Now what happens is that, of course, here you'll have iron chloride negative. The negative will come on hydrogen as the hydrogen stabilizes the ring. The same applies here. We're going to have the iron chloride will come on the hydrogen and the hydrogen stabilizes the ring, forming a stable ring with a methyl group and chlorine attached here, of course, plus HCl, then plus iron 3 chloride. The same applies here. We're going to form, actually, this is supposed to be on the 4th. So, implying that for this case, let us repeat it. For this case, it was going to be, now here we shall have our chlorine with our hydrogen. Then we bring our iron chloride, which iron chloride? Come on, hydrogen. As the hydrogen stabilizes, the ring. So this one will lead to the formation of the polar CH3. Don't forget a CH3, then Cl, yeah, plus HCl and iron 3 chloride. Alternatively, one can have it as can outline it alternatively as CH3, right? Of course, if it's reacting with chlorine and iron 3 chloride, you're going to have an ortho and a para, CH3 here, then of course plus HCl. Now, when you're outlining the mechanism of this alternatively, an alternative mechanism, one can first, because you're having two chlorine atoms, so you're going to react them with the iron 3 chloride. And this will give you chlorine partially positive and iron partially negative. So what happens is you'll have you can outline for separate product, but here even one can do it at once, CH3. Then you bring your Cl, which is partially positive, and your FeCl4 partially negative. Now what happens is that this one will come and this one will go. All right, so as that one happens, you're going to form, I can even make it two products like the other. I can form then I put here a plus. All right, then here I'll put my Cl. All right, then my methyl, of course. But on each, the chloride is going to replace the hydrogen. So shall have it like that. Now, even here, you can have the 1-on-4. All right, so still here you'll have your Cl and H. Now what happens is this one comes here and this one will also come there. Here you lose hydrogen, and even here you lose hydrogen, forming CH3Cl plus HCl. Then here you're going to form also CH3, but with a Cl down here and HCl. Or after having, because you have lost hydrogen, you don't form these. Since you have just lost hydrogen, you don't form. So you just stop it there. So you can outline it concurrently like that. Now, all other nitration, Friedel-Crafts acylation and alkylation, they all occur by similar reactions as for benzene. So that video of benzene can guide us too much, so that we really look at how these reactions are taking place. Now, in all these reactions, the 4 substituted derivative or the para-directive tends to be yielded in a greater quantity because it is sterically more favored product than this. Because here there is steric hindrance, the space between the groups, there is steric hindrance, but here the groups are too distant from each other. There is no steric hindrance. So since there is less steric effect, then we have it being more favored. Now, all other reactions take place like this and under the same reaction, like in benzene. So the video of benzene will help us too much. Now, a question can come. They can ask you explain why a full derivative tends to be in a greater quantity. Just you say that the reason is because of steric hindrance. You know, steric hindrance is the clouding of the large bulk groups around the reactive sites of a compound, and as such tends to slow down the reaction. So the crowding here between the methyl and the chloride and the chlorine group here, the space, there is some crowding. But from this first position and the fourth position, there is no much crowding. So that is what we can move on with. So nitration takes place in the same way, alkylation takes place in the same way, acylation takes place in the same way. Now, let's look at other reactions that this compound undergoes. And that one is going to happen in my next video.